Good morning, everyone. A confirmation about the audio, please. If the audio is clear and available, kindly confirm. Thank you. We shall be starting in a couple of moments, guys. Yes, Amrit, an earthquake occurred there. Srihari, UPSC eliminated elimination method, but look at the questions which have also been asked. And all of them, basically, if you take a look at it, many of those questions were on the expected lines. At least I can arguably say that for geography, and I can arguably say that for even environment and ecology. And if you take the case of mapping questions, if you take the questions from climatology, if you take the questions even from geomorphology, which was asked, was very much on the expected lines. And you had straightforward question. And please understand, all this aspect that UPSC has made it very difficult. The questions are becoming very random, everything accepted. But please understand, it is still a level playing field. It is still the best person on that day will succeed. And that is the point of the competition. So this time, basically, the cutoff is expected to go a bit lower, somewhere around 85 minus 2 to 3. So 82 to 85 is should be the expected cutoff as compared to the last time. So it will account for all those changes which have been brought about. To and fro. In what context are you asking about to and fro? To and fro means oscillation. In what context are you asking about to and fro, Kishan? UPSC prelims paper was discussed yesterday, Madhur, on YouTube. It was a live discussion which was held for around 3 hours and more. And you will be able to find that on the YouTube channel. Okay, regarding P and S wave. So it was a very direct question taken directly from the PPT. Take a look at the PPT and the annotations of the PPT, Kishan. You will get that exact line written in the PPT itself, right? About P wave and S wave, how we have discussed P wave and S wave, and we have drawn the diagram also. So any of you who has been attentive in the class would have immediately caught that particular sentence about the movement of the particles and also the movement of the entire wave propagation and why P wave travels faster. I'm sure the ones who have been sincere in the session, who have attended the session, not simply sat in the session, you would have basically observed that this P wave and S wave, we have discussed it exactly per se, word by word, letter by letter in the session. Exactly my point. Okay, so hello, a very warm good morning to all of you, and welcome to Baiju's Exam Prep IAS. Welcome to another session of geography. Now, here, last week we had finished with the portion of atmosphere and temperature. That is why now we will be initiating the portion of atmospheric circulation. So, on Friday, we had discussed and we have held the discussion about temperature, the aspect of variation in temperature, how temperature varies from one point to another, why temperature varies from one point to another. And also, we had taken a look at the factors such as insolation, temperature inversion, albedo, urban heat island, all those concepts that we have taken a look at. Now, that is going to be applicable, and that is something which we are going to apply in the portion of atmospheric circulation in order to understand the aspect of pressure development, what is high pressure, what is low pressure, and also why is it that the winds move, what are permanent winds, what are local winds. Those are the expected questions which appear from this area, and those are the portions that we are going to target. Now, by the way, even from the chapter that we covered about temperature, heating of land and water, if those of you who have seen the question paper would have observed that there is a direct question coming from that also, that why is it that there is a greater temperature difference between land and water during the summer. I'm sure you would have come across those questions. So again, that reinforces the belief that if you stick to the basics, if you cover the basics, you will be in a good position of confidence to cover the questions appearing in the prelims examination, rather than going for some random materials, rather than going for a very hi-fi kind of a preparation strategy. Sticking to the basics is very, very rewarding, and we have many of our candidates who have performed extraordinarily well yesterday, despite the entire mood being very gloomy that the paper was tough, etc. Many of our candidates have performed very well yesterday. So with that, we start with the portion of atmospheric circulation. Now for prelims here, this is relevant for your prelims as well as for mains. Yes, Madhumita, we'll discuss that. So for prelims, we have the questions about permanent winds, which are asked. Then we have the question about pressure belts, and also sometimes about names of local winds. Names of local winds. Oftentimes you get a kind of a statement based question about this, that this is the name of the local wind, where is it and which region does it blow over. Regions of existence. Then in the mains examination, generally you get questions in this area about the tricellular model of circulation. Okay, so we get an idea about the tricellular model of circulation, and it is not a direct question which is asked that as you would expect in your class 10th level or 8th level, that what is tricellular model of circulation. No, it is slightly bit complicated and a derived question which is asked in the mains, but mostly deriving around the simple concept. Now here we are going to study about atmospheric circulation, which is going to help you quite significantly moving ahead into the portion of other factors of climatology, be it jet streams, be it the aspect of El Nino, La Nina, be it the Indian monsoon, any other factor, be it the tropical cyclones, temperate cyclones, front formation. Most of the factors of climatology that we are going to come across, that is going to revolve around the tricellular model of circulation and the atmospheric circulation in general. So that is what we are going to concentrate upon. We are going to initiate with a very basic portion about what is pressure, and slowly and steadily we shall be building up the concepts to arrive at that particular concept. Now, without further ado, let us initiate the discussion, and let us first of all talk about pressure. What do we understand by pressure? So when you think about the term pressure, it ends up indicating the total amount of force exerted per unit area, right? The total force which is being exerted per unit area, that is pressure. Now, when we talk about air pressure or atmospheric pressure, so how do we get to know that, or what is atmospheric pressure? So over any region, over any particular area, the weight of the air column above it, right? The weight exerted by the air column above it, that gives you an idea about what is atmospheric pressure in that region. So that is basically the ideation of pressure. Now here, when we think about atmospheric pressure or when we think about air pressure, you have to understand and we have to look at certain concepts here. For example, let us suppose we have the ground surface, let us suppose, and here the ground has gotten heated up in this region. There is heating of land which is experienced here, let's suppose. Now, as the land gets heated up, the air above it will also end up getting heated, isn't it? Because it is in contact, so the air above it will also get heated. Now, when the air gets heated, the particles will get excited. The particles will start moving. Some of them will escape maybe this boundary that we have drawn. So eventually the air gets lighter. Anything which is lighter tends to rise up, right? We have seen that. And how long will it rise up? As long as the air is warmer than the surrounding, the air will continue to rise up, isn't it? It will rise up as long as it is warmer than the surrounding, because that is the time that it will be cooler. That is the time it will be lighter than the surrounding air. So that is why when it rises up on being warm, what is the condition of pressure? So let's suppose here, this is the ground surface and the air is rising up. We know that pressure is the force exerted on the ground surface, force per unit area. So if the air is rising up, what do you think will be the impact of pressure? Will the pressure be indifferent to it? Will the pressure increase on the ground or will the pressure decrease? What do you think? Good. So the pressure will decrease. So that brings us to the first conclusion, and that is basically rising air causes a low pressure. Rising air ends up causing a low pressure. Now, in another area, let's suppose you have cold air parcel which is present. Cold air which is present here. Now that cold air will have the particles which are very close to each other. When the air is very cold, that means it has got very less energy. That means the particles, rather than being in excited state, they will start becoming very static and will huddle together. So in cold air, the particles are very close. So that means the cold air is heavier. And when the cold air is heavier, it will start to sink. Now, what do you think will be the impact on pressure in this case? The impact on pressure in this case will be that as the air is sinking, it will lead to an increase in pressure. Very good. So that means sinking air causes a high pressure. Okay, sinking air causes a high pressure. So that is the very basics about pressure. Now, temperature is only one of the factors which contribute to pressure. Even wind movement can lead to variation in pressure. Let us drill that particular sentence into our mind and we will take a look at the other factors also. Okay, many of the times what happens is, before looking at the other factors, we always think that, okay, rising warm air means rise up will be low pressure. and there will be no other regions of low pressure. So pressure can be controlled by other factors also. Okay, so temperature is only one factor which induces a pressure difference. Difference in pressure. Okay, so that is the case where if the air gets heated up, it will tend to rise. If the air gets cooled down, it will tend to sink, and that is where it will end up influencing the pressure of the region. Now let us take a look at the basics. So weight of the column of air contained in a unit area from the mean sea level to the top of the atmosphere is referred to as atmospheric pressure. It is expressed in the units of millibar, and at sea level, the average atmospheric pressure is 1013.2 millibar. So here, if let's suppose an area has got a pressure of 1020 millibar, it will be always regarded as a high pressure. If an area, let's suppose, has got a pressure of around 1000 millibar, it will be regarded as a region of low pressure. So that is where the average atmospheric pressure is 1013. Above that, high, below that, low. But here also, please understand, it is not an absolute term. If an area has got a pressure of 1000 millibar and another region has got 950 millibar, so in comparison to that, this will be an acute low pressure or intense low pressure. Okay, so that is basically the aspect of atmospheric pressure in this case. Now, this atmospheric pressure, many of the times, induces a movement of air also, which we refer to as wind, right? Atmosphere in general is not felt by us, is it? We don't feel the weight of air imposed on our hand, imposed on our body, even though that pressure is very huge. And that pressure is very apparent. That what is the pressure that we are used to when, let's say, you climb a top of a hill or a hill station, or let's say in an aircraft where there is a kind of a poorly maintained pressure anyway, immediately your body starts behaving differently. If the outside pressure suddenly drops, you'll find that many of the times bleeding starts to get initiated from your ears, from your nose, and so on, because the body is very much used to the very high pressure that we experience on the ground surface and is not used to the low pressure conditions. So this pressure that we don't end up experiencing on the ground, we experience the atmosphere only when the air moves, that is wind. And wind will never come into existence if there is no pressure difference. So all that wind that you see, that you experience, that is basically air moving from a region of XYZ pressure to another region of different pressure. That is always be the movement of the wind. Now let us understand how this pressure induces that wind. So here, let us consider, for example, a particular area. Now here, let's suppose you have warmer air, okay? Warm air. Now this warm air, because it gets heated due to the heating of the ground, right now we are considering the temperature conditions only. As the ground gets heated up here, heated up, now the air will also get heated up. So the air tends to rise here. As you can see, the air tends to rise. It will rise as long as it is warmer than the surrounding. It keeps on rising. Now, at max, if you consider, the air will tend to rise at the level of tropopause. Very rarely will you find a condition where the air rises beyond tropopause. But air will tend to rise only up till tropopause. Why? Why is it that air doesn't rise above tropopause? We have studied about it. Because when we talk about the region of tropopause and beyond that, there the temperature is already very, very high. Okay? So that is why you will come across a scenario where at max the air is able to rise up to the level of tropopause. Now, tropopause acts as that upper kind of a ceiling which is present. And beyond that, stratosphere will experience a warmer condition, already very warm condition. So there the air will not end up rising too. So here, as it reaches the level of tropopause, this air then, let's suppose this is the tropopause, as it reaches here, it will diverge. It will diverge. It has got no other place to go. Have you ever seen the case where, let's say, there is a fire or you have burnt a bonfire and there is a ceiling on top? Observe how the smoke behaves. The smoke will rise up, hit the ceiling, and then it will diverge in all different directions, isn't it? Similarly, like this, here also, when the air tends to rise up, it hits the tropopause. Beyond that, it has got warmer air, so it doesn't go there. It simply diverges. Now, at the level of tropopause, that is at a height of 16 to 18 kilometers on an average 13 kilometers, suppose. What do you think is the temperature in general? Is the temperature high or is the temperature low at this region? What do you think? At this particular area. Very good. The temperature in this area is going to be very, very low, isn't it? Roughly in the range of minus 60 to minus 80 degrees Celsius. That is the temperature almost at the top of tropopause. So here, as this air has reached in this region and it has started diverging, in its motion thereby, it stays in that region for some time. It will start losing temperature. It will start becoming colder due to the influence of the surrounding air. It will become colder and colder. A point will come when it becomes so very cold that the particles they cling together. And when the particles they come together, the air becomes heavier. What will happen? If the air becomes heavier, it will straight away start sinking down. So that is where, as the air becomes heavier and colder, it simply starts sinking down. Now, as it sinks down, there will be a level of adiabatic compression which will happen. There will be a level of slight warming which will also happen. But nonetheless, if it is still cooler than the surrounding air, it will continue to sink down. In case that the surrounding air suddenly becomes very cold, it will not sink down any further and you have achieved a condition of temperature inversion, a subsidence inversion. But as long as it is colder than the surrounding air, it will continue to sink. Sinks down here, hits the ground. Now here, where it has hit the ground, what conditions of pressure will we experience? We will experience a high pressure. And in this region, we are going to experience a low pressure. Isn't it? Now, when we have the condition in the low pressure area, that the warm air has been rising up. Now, if for a moment, think about the entire region near the ground surface, just like a endless pool of particles, suppose, air molecules in the sense. Now, if you have a section of air which is rising up, that means what? On the ground surface, you have a vacancy which is created, isn't it? There is a kind of a vacancy created as the air has risen up. And subsequently, simultaneously, in this area of high pressure, we have more air particles hitting the ground. So in a way, in this region, we have excess of air molecules which are present. So here we have deficiency of air molecules in the region of low pressure because the air has risen up. And here we have surplus of air molecules because the air is sinking down. Anything will move from surplus to the region of deficiency. And that is where we experience the movement of air and air particles. Now, this movement of air and air particles, that is what we experience as wind. So, wind will blow always from a high to a low. Whenever there is a pressure difference, there will be an air movement to compensate for that pressure difference, always, regardless of what come may. Whenever you walk out on the road, or maybe you are standing in at your terrace or in your balcony or in front of your window staring down the street, whenever you experience a whiff of wind coming across your face, immediately understand that it is originating from a region of high pressure. It is moving to an area which is going to experience a condition of low pressure, always. So sometimes we experience that the wind direction changes, right? Let's suppose yesterday the wind was coming from this direction, today the wind is going from this direction. So that means the high pressure, the low pressure region, they are changing very frequently. So always, and that brings us to our second major conclusion, and that is winds will blow, always blow, from a high to a low. Or it can also be inferred as pressure difference induces a wind. Now here, I want you to think for a brief moment, just as an analogy of water. Now, in the case of water, water ends up flowing whenever there is a height difference. Whenever you come across a height difference, water will flow. Think about the pressure difference like this for a moment. Now, if let's say I keep a jar of water, or if there is water stored at the same level, there will be no flow. But if I increase the height of one and decrease the height of the other, I'm increasing the height difference overall, the flow of water will be initiated. So there also, let's suppose I'm taking a glass of water in my hand and I'm pouring it on the table here. Now the difference is not very much, but there is still a difference. So the water will fall, but it will fall with a moderate speed. Now suppose I take the same glass, I hold it up, and rather than the table, I pour it on the ground. It will fall with a slightly greater amount of force, isn't it? Because now the height difference has increased. Now suppose if I take that glass of water, I go to the third floor or fourth floor, and then I pour that water onto the ground floor. So in that case, what will happen? The force of water will further increase. So where am I getting at? Greater the height difference, greater will be the force at which the water will fall, isn't it? I hope we all have seen that. We all have experienced that. Now, similarly, in the case of pressure, greater the pressure difference between the two regions, stronger will be the wind movement. Weaker or lesser the pressure difference between the two regions, weaker and more feeble will be the wind movement which will be experienced. Okay, so that is again something we can write here. greater the pressure difference, stronger is the wind movement. Lesser the pressure difference means weak winds. Okay, so that is basically the aspect of wind and wind movement in general. Now, here, that means sometimes when we experience very strong wind movement, for example, during thunderstorms, or for example, we will come to those phenomena later on. For example, sometimes when you experience hailstorms. So, for example, in the region of Ahmedabad, for the past few days, you have hailstorms which have been occurring, where you have large particles of ice also falling on the ground surface. I'm sure in this is the month where in many different parts of the country you would have experienced this, or you would be experiencing this, where sometimes large particles of ice, they fall along with rain. Now that is what is referred to as a hailstorm. Now during those conditions, you would have experienced that the wind velocity is very, very fast, and normally in the day-to-day cycle the wind velocity is not that fast. So that basically means that during those conditions the difference in pressure is going to be humongous. That basically means that low pressure, whatever it is going to be very low, and the high pressure, that difference is going to be significant. We'll come to that also. But before that, we come to the different types of pressure. In terms of, we have said that pressure can get created by various factors. Temperature is just one factor which can impact the pressure. So basically, what are the other factors that we have? So we have the condition of thermal and dynamic pressure zone. So when we say a thermal pressure zone, these are the areas pressure is created due to impact of temperature. That basically means heating of land induces rising air, that induces low pressure. And that also means colder regions experience high pressure. So this is something that we have already taken a look at. Now, here, after this, when we take a look at dynamic pressure, what is that dynamic pressure zone? And how is that dynamic pressure zone created? So dynamic means what? Something which is moving, something which is stable and still, that is static. Something which is moving is referred to as dynamic, isn't it? Now let us think about certain conditions. Okay, just keep your mind free of any kind of prejudice or any kind of preconceived notion, and we will understand that. So here, let's suppose we consider the room that you are sitting in. Wherever, in whichever room you are sitting in, we assume that you are sitting at this point of time. So let's consider that room. Now here, in that room, think about it, that if I have installed fans here. On both ends at the ground level. I have installed fans. Now these fans, they are rotating and they are basically inducing a wind movement. Now here, when we have air which is being supplied in this area, air that is being supplied in this area continuously, it is not stopping. Now in that case, when the air is being supplied and from both the sides the air converges, what do you think will happen? Will the air start jostling over one another, that I will go on top, I will go on top? Will that happen? What do you think will be the resultant? The air will converge. It has got no other place to go in that case. So it will be forced to rise up. Here it will collide. It will be forced to rise up, isn't it? Because it has got no other possible place where it can go. It has got no other room left. So it will be forced to rise up because the air is consistently being supplied. As it rises up, eventually it will end up hitting the ceiling, isn't it? It will end up hitting the ceiling. Now, when it hits the ceiling, after that, what happens? After that, again, it has got no other place to go. So it will end up diverging in that case. One will diverge in this direction. Air will diverge in this direction. It will diverge in this direction. It will diverge in this direction, isn't it? So that is basically how the winds will behave in the sense in that closed environment. Isn't that the same? So here, if you consider this particular area, if you consider this particular region, so what do you think will be the impact of pressure here? Will there be a high pressure on the ground in this region, or will there be a low pressure on the ground in this region, in this area? What do you think? Air is rising up in this case. Very good. Perfect. Beautiful, guys. So in this case, here we experience conditions of low pressure. Why? Because we have rising air, isn't it? So because we have rising air column. So, rising air column. Okay? I hope that is clear. Yes, Paramita, beautiful. That is going to be the case. Okay? I hope that is understood. Okay, guys, let me tell you one thing very frankly. I hope that you don't mind it. So I get to see this trend. Many of you end up joining the session around 35 minutes late. And then the request is that please revise everything that has been done till now. I don't know what is the trend which you are following in the other subjects. Let me make it very clear. That is not going to happen for here, because in those 30 minutes, we might have covered a concept that will be very difficult to revise again. It will be time consuming. And also, please understand that all those candidates and the students who have been sitting there for from the first moment that the session started, what is their fault that they will have to go through it again? So please don't make that request, those requests. Now that the recordings are available, kindly go to and look at the recordings eventually if you want to get a clearer concept or a brief revision in that. Okay, and I hope that is understood and that message is received loud and clear, because we also here, you might not be aware about it. So that is why, just to tell you, we get an idea about each and every student when they have joined, when they have asked the question, when is it that they are leaving the session, rejoining again, and then again asking the question. We get that entire detail in front of us also, much more than what you can think of. So that is where, please, let's not have that kind of an environment that we keep on repeating the same thing again and again. I hope that is clear and that is well received. Now, after this, let us come to the other type of condition. The other condition, let's suppose here I have installed large fans, or large fans, in fact, the blowers near the ceiling. Okay. Now these large fans, they will be blowing here the air in this region. They will be blowing the air in this region. Now in this case, when the air collides, what do you think will be the condition here? Where will the air go? The air has got no other place to go. So the air simply sinks down, won't it? It will simply end up sinking down. Okay? It will end up sinking down here. Now, as it sinks down here, in this case, where the air will go? Again, it will end up diverging in this case. It has got no other place to go. So on the ground surface this time, the pressure condition will be high pressure. Beautiful. So on the ground surface, here you have the condition of high pressure. Now observe a few things here. No, not exhaust fan. Think about a large blower fan. Okay, you have sinking air. Now observe a few things here. Again, very quickly, let me tell you. Let's suppose you have large fans installed in the room near the ground surface. As these fans, they will end up blowing the air will collide, they will converge. It will have no other place to go but to rise up. So on the ground surface, as the air rises up on the ground surface, the impact on pressure will be a low pressure because you have a rising air in that region. So there will be no greater force applied on the ground, but rather force which will be uplifted from the ground. Whereas in the other scenario, if let's say you have air which is blowing from the, or which is given from the top of the ceiling, now that air converges. Imagine the room that you are sitting in. Look at the top of the ceiling and observe, if you have air which is coming from all directions on the top of the ceiling, what will happen? The air will collide, will have no other place to go, and it will simply sink down, isn't it? Now, when it sinks down, it increases the pressure on the ground, creating a condition of high pressure. So, in both these cases, even for a brief moment, have we considered the factor of temperature at all? We have not. We have not even talked about temperature in this case. That whether the temperature of the room is high or low, we have not even talked about it. So, what does that mean? That means that this low pressure or high pressure which is getting created, that is independent on the impact of temperature. So this kind of pressure which is created, that is referred to as a dynamic pressure zone, a dynamic high pressure, a dynamic low pressure. So this brings us to next set of conclusions. So here, let's assume convergence of air. Yes, Shalu, that is correct. Convergence of air leads to rising air column and creates low pressure. Convergence of air in which region? On the ground. Convergence of air on the ground. That induces low pressure. Then, convergence of air higher up, that creates a sinking, and then that sinking will hit the surface, and then it will create divergence on the ground surface, isn't it? So, divergence, or rather, sinking of air due to convergence higher up. There is a convergence in the second case happening in this region near the ceiling, isn't it? So there will be a convergence happening due to which the air will be forced down. So sinking of air due to the convergence higher up induces high pressure. Is that understood or not? Let me know. Nisarga, how can we say that temperature is inversely proportional to pressure? We have seen just now that temperature, it can be possible that temperature is not even dependent, or pressure is not even dependent on temperature. In this case, have we seen that pressure is dependent on temperature at all? No. So only in the case of thermal pressure zone do you have the conditions of temperature and pressure associated. Otherwise, you don't have that condition at all. Okay. Then pressure here is created due to movement of air. Yes, that is correct. Kishan, on one side you wrote, cold air experiences high pressure. Cold areas experience high pressure, yes. And on other side, you said, cold air by both sides crush and rise and creep. I'm unable to get the question here, Kishan. Are you saying that here I have said there is cold air in the second case? I have not said that. In case you have heard about it, please erase that. I have not said that there is cold air. I have not talked about temperature at all. In this entire second portion of dynamic pressure zone, this is independent of temperature. I have not at all talked about temperature in this case. Is that problem which still persists, or has that problem now gone? Difference between dynamic and thermal. So dynamic pressure zones independent of temperature. Thermal pressure zone controlled by temperature. Do you get that? Right? Cyclones will come to it, Mohammed, later on. Cyclones are created due to different conditions. Does temperature of sinking air go on decreasing from tropopause to the ground? Not always. Due to adiabatic compression, then the temperature would become very less, is already very low. So basically, Yatindra, what happens is that as the air sinks, let's say in the case of any condition, as the air sinks, it gets slightly compressed and slightly warmer, right? But there, if it is forced down, if it is forced down from above, and also as we saw in the case of the dynamic pressure, the air has got no other place to go. It will be deliberately forced down. So as long as it is forced down, or as long as it is colder than the surrounding air, it will continue to fall, it will continue to be pushed down. Okay. Why it is called dynamic? Dynamic because this pressure zone is created due to movement of wind, nothing else. And Prithvi, understand one basic concept. What is pressure? Pressure is the weight imposed by the air column on the ground surface. First of all, get that thing very clear. That when you hear about pressure, what is pressure? The weight imposed by the air column on the ground surface. So in any place, if you have rising air, that means what? Any place where you have rising air means what? On this region, the amount of pressure which is exerted has become lower because the air has risen up. So anywhere where you have rising air, the pressure will get lower. Any region where, let's say, you have sinking air as in the air sinks and hits the ground. So in that condition, what will happen? It will exert more force, so more pressure. So sinking air, wherever there will be a high pressure. Wherever you have a rising air, you will have a low pressure. Is that understood, Prithvi, that why in this case we have high pressure on the ground? Because here the air which is moving closer to the ceiling, it has got no other place to go but to sink down. Okay, perfect. Now, what is the temperature aspect in this movement of air? There is no temperature aspect in this movement of air. No temperature. Means in second case on ceiling, there is low pressure. Yes. On ceiling here, there will be low pressure. Yes. Is that understood? In Abhishek, in pick one, there is lower pressure due to rising of air towards upper side. Then what about the pressure on the upper side? It will be higher pressure. Yes, correct. And shall converging and rising air causes low pressure, sinking and diverging air causes high pressure. Correct. Abin, why air doesn't rises or get obstructed at troposphere or entropause? Abin, that is because of the case that, see, whenever you talk about the air which rises up, it will rise up in many of the cases to a point where the air is slightly cooler than the surrounding. Now, as you enter the tropopause and beyond in the stratosphere, the air gets much warmer. You have a negative lapse rate. So the air will get much warmer. Warm air tends to stay up, cold air tends to stay lower. So that is where the air doesn't simply enter into the stratosphere. Sometimes you have, let's say, a volcanic eruption, for example. Now, volcanic eruption will have significant amount of clouds which are risen up and which rise up maybe to a height of 100 kilometers in certain cases. So that will puncture through the tropopause, through the stratopause also. And you have certain rare cases where the air tends to puncture into stratosphere, but that is not something that we experience under general circumstances. It is a very rare case. Okay. Yes, Bhavna, that is correct. If it's warm during sinking, then it don't create. Whenever the air is sinking, it will create a high pressure. Rising air will always create a low pressure. Okay? Right? Pressure is basically the force induced on any surface area. And why the wind not did not go under subduction, as in where will the wind go under subduction? In which case, Amit, do you think the wind should go under subduction? You mean that it should puncture the ground surface and start going down? Is that what you say? Yes, Vivek, that is correct. Second portion, creating low and high pressure due to fan. Yes, Jyoti, that is correct. Okay. Why, sir, in one case airflow in the ground to the upside and second case airflow upper to low? So that means for a brief moment of around half an hour, something has been switched off in that case. That is why now you're asking why this diagram that you're drawing, that air is rising up in certain case and air is sinking down in certain case. What is this? Basically, it is due to the, I have said here, let's say the air is blowing. If you have installed fans and the air is basically blowing on the ground surface, it will converge, it will rise up. If the air is blowing on top, it will converge and sink down. Okay, I understand the problems of the morning sessions that many of you face staring at the screen when the fans are on or the air conditioners are on. I understand that there is a lot of pressure on the eyes also, right? It is as if there's a high pressure created on the eyes and the eyes are about to get shut down. So, and it gets very apparent many of the times with the question factors also. But please try to hold up. Please try to carry on, because this is a portion which is going to help you in many other areas of climatology also. Okay. Now we come to the portion of isobars. What are isobars? So isobars indicate the these are those imaginary lines which end up joining places exhibiting equal pressure. Just like in the case of isotherms, we had isotherms joining those places indicating equal temperature. Isobars are those places which join places of equal pressure, right? So anywhere where you observe, let's say 5 areas. Now, if they exhibit a similar pressure, the isobar which will be drawn will be something like this, right? And that isobar, let's say of 1,000 millibar, that means every place on this will have 1,000 millibar. Example, suppose here, observe here, the isobar over the region of India in the month of July. So observe here, you have this isobar representing 997, this isobar representing 998 millibar, this isobar representing 1000 millibar, this isobar representing 1001 millibar. Now there is a pressure difference of 1 millibar in this particular case, which is indicated by the isobars, isn't it? Now, how close or how far these isobars are, can that give us an idea about how quickly or how slowly the pressure is changing in a region? We can get an idea. For example, let us suppose I give you two conditions and I give you two cases. Let's suppose. Now, in both the cases, here, the distance is, let's say, 100 kilometers between them, between the two ends, let's suppose. The distance is 100 kilometers. Now, in the first case, each isobars, let's suppose, indicate a variation of 5 or 10 millibars, let's suppose. Let's suppose this is 1020 millibar, and this will be 1010, 1000, and so on. Let's suppose here this will be how much? 1010, 990, 970, 960, 950, right? And in this case, if the isobar is let's suppose like this: 1020, 1010, 1000 millibar. So here in the figure A and figure B, both of them, the pressure is reducing from one end to another, isn't it? Now suppose I consider this as point 1 and I consider this as point 2. Here also I consider this as point 1. I consider this as point 2. So as we move from 1 to 2, in both these cases, the pressure is reducing. But then the pressure is reducing more drastically. In which case? In the first case, isn't it? In the case of A, the pressure is reducing. Whereas in the case of B, the pressure is reducing, but it is not reducing at the same rate. And that is indicated by the isobars also. So this variation in pressure over a particular distance, that is what is referred to as pressure gradient. Okay, so this difference in pressure over a distance, that is referred to as pressure gradient. Pressure gradient, which basically means difference of pressure over a distance. That is referred to as pressure gradient. Now, here in the first case, can we say that pressure gradient is high as compared to the second case? Because that difference in pressure is going to be higher in the first case as compared to the second case. So here we can say higher pressure gradient. So let us come to a conclusion in this case. If the isobars are closer to each other, pressure changes quickly, and that also means pressure gradient is high. Isn't it? So just by looking at the arrangement of isobars, we get to know about pressure gradient. If the isobars are far away from each other, that means pressure is changing very slowly. If the isobars are very, very close to each other, means the pressure is changing very quickly. Now, we have seen and we have talked about it that wind moves and wind blows from a high to a low. And we have also taken a look at the basic conclusion that greater the pressure difference, stronger will be the wind flow. Weaker the pressure difference, weaker will be the wind flow. We have looked at that. So this pressure difference or this pressure gradient in itself induces a force of movement for the wind. And that is what is referred to as the pressure gradient force. So when you have a difference in pressure, wind will be initiated. Greater the difference, stronger will be the wind. Lesser the difference of pressure, weaker will be the wind. So that means the difference in pressure or the pressure gradient is an important factor in wind. So due to that difference in pressure, the movement of wind is initiated, and that movement is initiated by what is referred to as pressure gradient force. So if we have pressure gradient or other way around, if we write it, wind speed is directly proportional to pressure gradient. Wind speed is directly proportional to pressure gradient. And whenever you have a pressure gradient, it induces a wind movement by a force referred to as pressure gradient force. So, stronger the pressure gradient, greater will be the wind speed and vice versa. Now, I'll ask you one question which I've asked earlier as well. That is, what do you think? Can these isobars crisscross each other or no? Very good. This isobar will never crisscross each other. Because if they crisscross each other, again, the same argument as we put in the case of isotherms. Let's suppose we have an isobar of 1000 millibar. Let's suppose we have an isobar of 990 millibar. So in this region, that means you have two different pressures at the same time, which is not simply possible. Pressure does vary between day and night. Isobars may vary in their pattern between day and night, between one day and the other day. For example, the isobars that you might end up observing today from the satellite map will be very different from the isobars, let's say, if you look at it tomorrow. Not very different, but will be different. The isobars that you take a look at 1 month from now will also be substantially different. Same is the case with isotherms also. So that is basically the aspect of isobars and pressure gradient. Okay? Now, after this, here, pressure gradient is a change in pressure with horizontal distance. How is it that the pressure is changing? Greater the pressure gradient, stronger is the wind. Weaker the pressure gradient, weaker is the wind. Just understand that aspect. So if over the same distance, let's say, if we consider this distance, if there is greater difference in pressure, pressure gradient is high. Gradient is what? A difference. That is what is a gradient. Even in the case of slope, we have talked about gradient, steep gradient, shallow gradient, etc. So greater the gradient means the pressure difference is going to be high, means stronger wind. Now we come to the factors which will influence the velocity and the direction of the wind. Because you would also have experienced that wind movement is not always consistent. You would have experienced that during certain seasons, the wind is almost absent. During certain conditions, the wind moves very strongly. You would have observed that during certain conditions, the wind comes from a different direction. During certain conditions, wind comes from a different direction. So there are factors which contribute to the movement and velocity of the wind. Now, amongst those factors, you have the three major factors, or the most important factor rather, is the force of gravitation. And the gravitational force basically means that it will keep the winds stuck to the ground. Right? Movement of air is oftentimes closer and hugging the surface of the ground. Now, the three forces which are responsible, three major forces responsible for impacting the velocity and the direction that the wind takes is basically the pressure gradient force, the frictional force, and what is referred to as the Coriolis force. So these are the three forces which are responsible for the velocity and the direction that the wind takes. So let us take the case of each one of them. Let us try to understand what are these forces. Okay? When two isobars are near then higher pressure gradient, that means pressure is changing much more quickly, isn't it? That each of the isobars represent different pressure. So if one is 990, the other one is 980, and they are very close to each other, means over a small distance from 990, it is reducing to 980. Whereas if 990 and 980 are very far away, that means it takes a long distance for the pressure to change by 10 millibar. Okay. Now let us start with the pressure gradient force. So the rate of change of pressure with respect to the distance is the pressure gradient at the same elevation. So basically, the force induced which initiates the wind motion due to the difference between the high pressure and the low pressure, that is what is referred to as the pressure gradient force, or simply put, PGF. So this is basically the pressure difference which is induced, and that induces a wind movement with a force, that is the pressure gradient force. Winds will always blow from a high to a low. Winds will always move from a high pressure to low pressure. Regardless of whether any kind of pressure we talk about, that is the only kind of wind movement that you come across, from a high pressure to a low pressure. Always, in every circumstance, high pressure to a low pressure. Okay? Now, let us take a look at the example of it, that how the pressure gradient induces the velocity of the wind. So, for example, what have we seen? We have seen that if the isobars are close to each other, means the pressure is changing very rapidly. That means the pressure gradient will be high. If the isobars are very far away from each other, means pressure is changing very slowly, means the wind velocity will be slow. Let us take a look at the application of it. So here you have the isobaric representation over the region of North America. Now, over the region of North America, here you will observe you have an intense low pressure around 988 millibar. And here you have high pressure, isn't it? So here you have high pressure and here you have low pressure. So if you observe the isobars in this region, so here, what do you think is the pressure difference in this area? Pressure gradient rather. Pressure gradient there is shallow. It is not significant. It is basically less, isn't it? Why? Because isobars here are far away from each other, so we get an idea that, okay, the pressure difference must be less, pressure gradient must be less. So if the pressure gradient is less, observe the wind which is initiated will be slow, weak wind. And suddenly, if you observe that here the isobars are very close to each other, means the pressure is changing very rapidly. As the pressure is changing very rapidly, means what? You have a steep gradient. That means suddenly the winds will accelerate, right? So wherever the pressure gradient is going to be higher, there will be very strong wind movement. Wherever the pressure gradient is going to be lesser, shallower, wind movement is going to be very weak. Is that portion clear? Jigar, in the case of northern area, you have different conditions of pressure. We'll come to it when we come slowly and steadily to the portion of climatology as we progress. You will understand. Shabir, what is it that you have not understood? Point that out. Okay, be particular in that case. Anjali, pressure gradient induces a pressure gradient force. Shivani, please do ask the question. What is the question that you have? How it moves from high to low, the pressure. So that is what we addressed in the very first slide of the day. That wind will move from a high to a low because higher pressure is an area of excess and lower pressure is an area of deficiency. If I take you back here, if I take you back in this case, low pressure region, if you observe, you have fewer particles. High pressure region, you will observe, has got excess of particles. So particles will tend to move from a high to a low, and that is basically going to induce a kind of a wind movement. How to flow these differences? Which differences do you want to flow? And why do you want to flow the difference? What is the question here? I'm unable to understand the question, Shabir. Please clarify that. Why isobars are circular in shape? Isobars, they can take any shape. Here, if you observe, what are the shape of the isobars? The isobars are like this. Suppose in this region again, you have around 1000 millibar. Isobar can be circular in shape. Okay. So here, let me write it down. Steep gradient means the pressure changes significantly. Why pressure gradient is very high? Pressure gradient is very high if the pressure changes very significantly, very frequently. That can happen due to temperature, that can happen due to movement of wind. Pressure gradient is, so think about it, that you have a high pressure, you have a low pressure. Let me write it down in a kind of a point-wise fashion, in a very old-fashioned manner, so that we are able to internalize it. So winds will blow from a high to low, which means winds blow from a high pressure region to low pressure region. And while I'm writing it, please focus on the concept. Don't think about it that he's writing it, so basically we'll get the annotation, so that will be more than sufficient. Don't think about it. Pay attention here on the step-by-step procedure here. Okay. So here, winds will blow from a high pressure region to a low pressure region. Now, in this case, can we say if the difference, or rather, the difference between the high pressure and low pressure Shubhangi, for your question, I will have the simple counter question for you. Does isotherm have an impact on temperature? Let me know. Shabir, in that case, I would suggest to you kindly look at the recording of the session. If we have no clue that what is isobar, what is pressure, then kindly take a look at the recordings. You will get an idea from the very initial portion. Okay. So the difference between the high pressure and low pressure in this case initiates the wind movement. Now, greater the difference in pressure, stronger is the wind movement. Okay? Any doubt in the portions that I have written up till now? If yes, please ask. Any of you. Any doubt in the 3 sentences that I have written now, up till now? Not other than that. Any of you. Okay, Masood, the greater the difference in pressure, stronger the wind movement. So here, think about it in the concept. For example, have an analogy with the case of water. Now, here, suppose I take a glass of water in my hand, suppose, and let's suppose, or I have water column at the same height. Now, water will not end up flowing at the same height, isn't it? When you provide a difference, that is where a height difference, that is where the water will start to flow. Now, suppose I have held the water at a particular height, I am pouring it on the table. The water will flow with a speed because it has got a height difference. Now, suppose I take the same water, go at a higher elevation, and then throw the water, it will flow with a greater speed because the height difference is greater. So, greater the height difference, greater is the flow of water. Wind moves with the difference of pressure. So, greater the difference of pressure, greater will be the wind movement. Okay? Is that understood? Right? Now, after that, here, difference of pressure over a distance, that is referred to as pressure gradient. Difference of pressure over a distance is referred to as pressure gradient. Now, pressure gradient induces wind movement clear. Pressure gradient will induce a wind movement. Now, this movement is induced by the force which we refer to as pressure gradient force. Pressure gradient force. So, greater the pressure gradient, greater pressure gradient means what? Greater difference between high to low pressure in the same distance. That means very high or very large difference between high pressure and low pressure. That is the greater pressure gradient. That means very strong winds will blow. Now let us take a look at the map here. So when you take a look at the map here, the isobars represent what? A particular kind of a pressure. Each isobar will represent its own individual pressure that it will represent there. Now, in this case, here if you will observe, you have a condition of high pressure. Around 1036 millibar is present in that area. Here, if you will observe, you have 988 millibar. That is a low pressure. Winds will blow from a high to a low. This will be the wind movement. But across this entire distance of 1,000 and more kilometer, because think about it, this is almost, as per the map, this is around the region of border of Canada, northwestern part of United States. This is the eastern coastline of United States. So over this thousands of kilometer, do you think that the wind speed will be consistent or the wind speed will be variable? It will vary, but it will vary depending on what factors? Depending on the factor that how frequently or how significantly the pressure is changing, right? So wind speed is dependent on the rate at which the pressure is changing. Let me write that down. Wind speed changes with respect to the rate of change of pressure. Okay? And that rate of change of pressure can be expressed by the isobars. So if I consider this particular distance, let's say of 100 kilometers or so, or let's say 500 kilometers. Let's say this distance is of 500 kilometers and this next distance is also of 500 kilometers. So in the stretch A and in between the stretch B, where is it that the pressure is changing very significantly? The pressure is changing very significantly in the case B, isn't it? Because in case B, here you had 1028 millibar. Observe, here you have 1004 millibar. So almost by 24 millibars, the pressure has fallen. In this case, here it was around 1036 millibar. Here it is 1028 millibar. That means the pressure has fallen across that same distance of 500 kilometer only by 5 or 8 millibar. So in the region of A, over a distance, let's suppose of 500 kilometer, pressure changes by how much? It changes by 8 millibar. In the region of B, again, let's assume over a distance of 500 kilometers, the pressure changes by 24 millibar. So the pressure gradient is going to be higher in which case? In the case of B, isn't it? So B will have higher pressure gradient. Higher pressure difference, for example. So B in this case will exhibit a higher pressure difference because the pressure is changing very rapidly. Now, greater the pressure difference, just like the flow of water. If the height difference is greater, the speed of water flow will be higher. If the height difference is less, speed of water flow will be less. So greater the pressure difference, stronger will be the wind. So in this case, we say we will experience weaker winds? And in this case, can we say here we will experience strong winds? Okay. So that is basically how pressure gradient force is an important factor when it comes to contribution to the wind movement. Okay. Now, then we come to other force. Now, that other force that we come to is the Coriolis force. Now, this Coriolis force basically is an apparent force. It is referred to as an apparent force. That means if, let's say, something is static on the ground or something that is fixed to the ground, it is not going to experience this force. Anything which is moving in an independent manner, for example, the ocean currents, for example, the wind movement, for example, let's say an airplane or a ballistic missile that you have launched, all of these, they are moving independent to the ground. So they will experience that Coriolis force. What is this Coriolis force? And why is this experienced? So Coriolis force here refers to the force induced due to rotation of the planet around its axis. And we do know, we have seen it in the first module itself, that because the planet is spherical in shape, the speed of rotation at the region of the poles will be very different than the speed of rotation at the region of equator. which will be very different than the speed of rotation here, which will be very different than the speed of rotation in this place. We have looked at that. So Coriolis force describes the pattern of deflection taken by the objects not firmly connected to the ground as they travel long distances around the Earth. This is induced due to rotation of Earth. Now, rotation of Earth basically means that different places will have different rotational velocity. We have looked at that. So, speed of rotation is highest in which place, by the way? Speed of rotation is highest where? Good. So, speed of rotation is highest. Is it at the poles? I have 4 of you who have said poles. Speed of rotation is highest at equator and lowest, that is 0, at poles. Okay? Because at equator it covers the largest distance in one rotation. At poles, the movement is almost 0. So the key to Coriolis effect lies in the Earth's rotation. Specifically, Earth rotates faster at the equator than it does at the poles. Earth is wider at the equator. So to make a rotation in one 24-hour period, equatorial regions move at a speed of nearly 1600 km per hour. But the region of the poles, here you have a movement of close to 0 km per hour, because as it rotates, take a globe, for example. Look at a globe. In the region of the globe, if you rotate, the region of the poles. Now, in the globe that you would have observed, the poles are fixed. So regardless of how much you rotate, the poles are not moving at all. That is a similar case in the case of planet Earth as well. So here, if you have, let's say, an object which moves from here to here, or here to here, or here to here, or anywhere, can we not say that the object is moving in between places exhibiting different speeds of rotation? We can say that the object is moving in this case, in the earlier scenario, moving between places indicating different speeds of rotation. Different speeds of rotation. No, it doesn't cause cyclone. Coriolis force is important for cyclone, but it doesn't cause cyclone. All of us are so very eager to understand cyclone. Ever since I started climatology, the first thing that I was talking about, I remember when I was talking about 3 classes back about water vapor, I got a series of questions. Does that cause cyclone? Then I talked about the factor of temperature and insulation. Immediately, does that cause cyclone? Then after that, when I talked about the factors of heating of land and water, does that cause cyclone? Then after that, when I was coming about temperature inversion, does that cause cyclone? And now today, since the first session itself, I'm getting endless questions. Even when I'm talking about high pressure, low pressure, does that cause cyclone? If there is a wind movement, does that cause? We will talk about what causes cyclone. I will talk in significant detail. I will go give you the images of the cyclone also. I will show you the three-dimensional picture of how the cyclone is created. I will tell you right from the basic that where that cyclone is formed. But till that point of time, let's try to hold our horses and let's try to understand what is being covered. Okay, when the cyclone will come, we will talk about it in significant detail. Is there any highest or lowest millibar limit? No. Okay. Right. So I hope we can have the patience till we come to the portion of cyclone, because before that we have many concepts to cover. Okay. Is there any impact of topography and altitude on PGF? Yes. Coriolis force is not making sense to me because we have not even talked about Coriolis force till now. We have only talked about whether it causes cyclone or not. It does not cause cyclone. And the other factor that we have talked about is that why it is induced. Okay. Now, object is moving between places indicating different speeds of rotation. Now, due to this, object deviates in its path, where it will bend to the right in the northern hemisphere, where it will bend to the left in the southern hemisphere. Why? Why that deviation will happen? Let us try to understand. So here we take the very famous car example that you would have come across multiple times. So we take the first case. Let's assume you have two cars. Now I'm sure by this time in your life, you would have at least moved in a car, observed the surrounding areas also. Now let's suppose both these cars are moving at a speed of 30 kilometer per hour. Let's suppose. Now, you would have also experienced that when you are moving on a road, another car, let's suppose, or when you are moving, when you are riding motorcycles or scooters or cars with your friends, you will always come across that scenario that many of the people, they have the habit of talking while they are moving on the road. They have a good long conversation which is happening, and both the motorcycles will be moving at the same speed, at the same level. So for one person, the other person is actually static, moving parallelly with that person. So imagine that in the case of a car. So here, let's suppose a ball is thrown from this car. We consider this car A, we consider this car B. A ball is thrown from this car. Now, this ball, because car B is also moving at the same speed, will be received by car B, right? So this ball, what do you think? Will it fall ahead? Will it fall behind? Or will it be received? Obviously, it will be received, because if it is moving at the same speed, then for the person sitting in car A, it will appear as if the car B is also coming along with them. So if you throw the ball, they will be able to catch the ball. Isn't it? Now, the second case. Let's suppose car A and car B. This time, car A is moving at a speed of 30 kilometer per hour. Car B is moving at a speed of, let's suppose, 120 kilometer per hour. Now this time, if the ball is thrown by an individual from car A, now, do you think it will be caught by the person who is sitting in car B? No, isn't it? Because here, when by the time the ball reaches here, car B would have moved significantly ahead. It is moving at a much faster speed. It would have moved somewhere here by that time. So an individual who is, let's say, standing there, having a jolly good time on the road. So here, what that individual will notice? That person will notice that the ball has fallen behind car B, isn't it? So that brings us to a set of conclusions. Or let's consider the third scenario also before coming to conclusions. So here, if I have car A this time moving at a speed of this time, if I have car A, car B, car A, let's say, is car B is moving at 30 kilometer per hour, and this time car A is moving at 100 kilometer per hour. So as here someone throws the ball from car A, what happens? Will it fall behind B? Will it be caught by the person sitting in B? Or will it fall ahead of B? What do you think? In front, isn't it? It falls ahead. It tends to fall ahead in this case because car A is moving at a very incredibly high speed. Car B is moving at a very slow speed. Now that brings us to the set of conclusions. First conclusion. When objects move between similar speeds, there is no deviation. When the object moves between similar speed, there is no differentiation or no deviation. Then, in the second case, when the object moves from a slower speed to a faster speed, the object falls behind. Falls behind. Okay? Then, the third case. When an object moves from faster to slower, speed, it falls ahead. Okay? Is that clear? Is that understood? So let's take this as the first case, this as the second case, this as the third case. And let us implement it on the planet in the entirety of the planet Earth. So here, when we talk about the planet shape is slightly that of a geoid, means bulged around the region of equator and flatter around the region of the poles. Now this is the region of, let's say, equator. Now, around 5 degree north or south of equator, the radius of the planet will be almost similar. There is a bulge which is happening. So the 5 degree north or south of equator, the radius of the planet will be almost similar. Let's consider the central portion or the central line that we have indicated. Let's consider that to represent equator. Let's consider this to be the equator. Now let's consider few portions. Here we have B. Here, if I consider A. Now, if an object, and listen to this very carefully, I will give the break immediately after this, don't worry. So, if here we have the condition that an object tries to move from B to A, let's suppose. It has originated from B. It tries to reach A. Now, speed of rotation is fastest at equator and 0 at poles. We know that. Speed of rotation is fastest at equator and 0 at poles. Now, in this case, if an object is moving from B to A, can we say it is moving from a region of slower speed to a region of faster speed? We can say that. And what did we conclude from that? When the object moves from a slower speed to a faster speed, it falls behind. So here, this object, rather than falling at A, it will end up falling somewhere here, A dash, isn't it? So that will be a movement to A dash. The converse of it. Let's say an object is trying to move from A to B, means from faster to a slower. So in case that it is trying to move from a faster speed to a slower speed, it falls ahead. So here, rather than reaching B, the object will move somewhere here, B dash. That is where the object will fall. Now, what is this deviation? In which direction is the object deviating? If you observe, in both the cases, it is deviating to the right. Okay, so in order to look at the deviation, always take a look at the source. From the source of origin, if you take a look at it, it will give you the deviation to the right. Now, here, let's suppose I consider here D, I consider here C. Okay, now here again, an object is trying to move from C to D, means slower to faster speed, means it will fall behind. So rather than D, it will reach somewhere here, D dash. It will reach somewhere here, D dash, isn't it? And then let's say from D to C, that means from a region of faster velocity to a region of slower velocity, it will fall ahead. It will fall here. C dash. Now what is this deviation? This is the leftward deviation. The movement is bending to the left in this case. Whereas in the northern hemisphere, the movement is to the right. That is why, because the objects are moving in between different speeds, that is why you have left deviation in the southern hemisphere and you have right deviation in the northern hemisphere. Now, let's assume an object is trying to move from here, point 1, to a region of point 2 in this case. Let's assume from point 1 to point 2. So that is roughly around 5 degree north to 5 degree south. 5 degree north latitude to 5 degree south latitude. Now, if it is moving in between this region, we can also say that here the radius will be almost similar in the case of 1 and 2. If the radius is almost similar, speed of rotation will also be almost similar to that of equator, isn't it? Equator, 5 degree north, 5 degree south, very close to each other, almost similar radius. So, when they have a similar radius, means the speed of rotation will be significantly similar. Now, when we have the speed of rotation as similar, there is no deviation which happens, isn't it? So an object which will move from here to here or vice versa will experience no deviation. That is why at equator, no deviation. And that can be represented as Coriolis force is 0. What about the region of poles? Let's consider this as the region of the poles. Now the speed of rotation at the poles is zero, isn't it? The speed of rotation at poles is equal to zero. So if you consider any other area, even in this area, any area, now difference in speed between the different regions and the poles is going to be very high because speed of rotation at the poles is absolutely zero. So any area which is moving even at, let's say, 100 kilometers per hour, the difference in speed is significant, isn't it? So as a result of that, because the difference is very significant in the polar region, the deviation will be maximum. So that is why Coriolis force is going to be maximum at the region of poles. So wherever we have difference in speed is greater, means deviation will be higher wherever, isn't it? Now, as at the region of poles, speed is zero, means from any latitude in comparison, difference in speed will be very high, isn't it? That basically means Coriolis force is the highest. Coriolis force is the highest. Okay? Now, the region at equator, no deviation, because here they are moving at similar speeds. Around this region of equator, they are moving at similar speeds. And that is why whenever you encounter a difference of speed, the objects will either tend to fall ahead or fall behind. Okay? Akula, why the deviation will exist at poles? Because of the same reason that I have written here. Wherever you have difference in velocity, at the region of the poles, the speed of rotation is zero. So even if you are moving from any latitude, there will be a significant difference in speed. So objects will tend to have a deviation. Okay? One of the reasons for slow movement of wind at equator is absolutely zero deviation of wind. Absolutely not. Bhavya, in the southern hemisphere, aspect is wrong. As if the origin point is D dash to C dash, which means from faster to slower, then why have you stretched a line behind instead of above? What? As the if the origin point is D dash. Origin point is not D dash. Origin point in this case is D and C. They are the origin points. From D, it is trying to go to C, and instead it is reaching C dash. From C, it is trying to go to D, and instead it is reaching D dash. What is the role of Coriolis force? So any wind which is moving, the Coriolis force basically ends up deviating it to the right in the northern hemisphere. Any wind which is moving, the Coriolis force bends it to the left in the southern hemisphere. If the speed at the poles is 9, if the speed at the pole is not 9, speed of at poles is 0. So see, any object which is simply present, any wind which is or air is directly present at the region of the poles, they will not experience deviation at all, unless and until you have a wind which is moving from polar area to here or from another region to the polar area. You will not experience deviation. But if a wind is moving, let's say from 60 degree to 90 degree, in that region 60 degree would be rotating at, let's say, 200-300 kilometer per hour. Poles will be rotating at 0. So the difference in speed is how much? Difference in speed will be 300 kilometer per hour. So that difference in speed means an object which is, let's say, moving at a slower speed, an object which is moving at a faster speed, things will fall ahead or behind. So while moving towards the poles, while moving away from the poles, that is when you experience Coriolis force. An air which is simply present at the region of the poles, that will never experience Coriolis force. Amit, yes, it is an exponent of relative velocity, but many of us, we don't have an idea about what is relative velocity, hence that longer explanation. Okay, so that is basically the aspect of Coriolis force. So it deflects the winds to the right direction in the northern hemisphere and to the left in the southern hemisphere. Deflection is more when the wind velocity is high. It is maximum at the poles and is absent at equator. And then the Coriolis force acts perpendicular to the pressure gradient force. How and why? So for example, you have a high pressure in the northern hemisphere, you have a low pressure in the southern hemisphere. So the pressure gradient force will be in this direction, isn't it? That will be the direction of the PGF, the pressure gradient force. If it is in northern hemisphere, it will try to bend to the right. Coriolis force will be acting in this direction always. And that is why the resultant wind will take somewhat in middle. Resultant wind. That is your northern hemisphere. Okay. So now we take a break. We take a break of 10 minutes and we will be back after 10 minutes and then we are going to continue. No, Amrit, I won't uh, do that atrocity of discussing frictional force. I think many of the people will simply stop breathing if we don't give a break right now. So here we take a break then and we get back in 10 minutes and we continue. Yatindra, it is due to relative velocity, right? There is no force as such, like no acceleration, no. So be back after 10 minutes and then we continue. A confirmation about the audio, please, guys. If the audio is available. Thank you. So now we come to the next kind of force, that is the frictional force. In very simple terms, force of friction is the force of resistance. Resistance offered in the path of the movement of the wind. Now, when there is a resistance offered, the speed will reduce quite significantly. Always. Isn't it? Now, here, if you consider, let's suppose a particular area or a particular region, let's suppose here, which has got a slight hillock also, buildings, trees, everything are there. Now, as the wind tries to move in this region, it will experience that force of resistance always, isn't it? And due to which the speed will be slow. But at the same time, if you consider a wind which is moving, let's say at an elevation of 3 kilometers, 4 kilometers, let's suppose, wind is moving at that elevation. Now, if the wind is moving at that elevation, it will experience lesser resistance. That is why speed is higher. That is why the speed is higher, isn't it? Now, if you consider another area, let's suppose here you have the land area and you have the nearby sea surface. Now, over the land area, you can have various different types of factors and influences, growth, hillocks, etc., which are present. Over the sea surface, you don't come across these factors. So if you have to consider the wind velocity will be higher where? Over the sea surface. Because the frictional force is minimum over the sea surface. So that is why the speed will be high. That is the reason why, in general, when you consider the southern hemisphere, in the southern hemisphere, the wind velocity or the wind speed is much higher as compared to the northern hemisphere. Because the southern hemisphere is dominated by water bodies, whereas the northern hemisphere is dominated by land area. So here, this is the reason why wind movement is very high, or rather not movement, wind speed is very high in the southern hemisphere as compared to northern hemisphere. Okay, so why frictional force is low over the sea? That is because over the sea, do you have any obstruction? Please understand. I hope we understand the meaning of friction by this point of time in our lives. Friction is something that is the force of resistance. Frictional force in simple is force of resistance. Any of us who are not aware about what is friction? Good. That is force of resistance. Resistance offered by the objects which are present on the ground. So, for example, if you have the wind which is moving here, then near the ground surface, here, what do you observe? You will observe that near the ground surface, the wind will encounter the trees, the hills, etc. So there will be a lot of things of resistance. There will be buildings in the in the way, etc. So there will be a lot of resistance. So as a result of that, the wind speed will slow down near the surface because of the resistance offered. But when you consider the wind at a higher region, at a higher altitude, the wind speed will not face that amount of resistance anymore. You don't have those objects of resistance anymore. So wind speed will be higher at an altitude, wind speed will be very slow at the surface. Is that understood? Samarjit, you had that question. Is that understood? That wind speed, why is it slow at the surface? Because at the surface, you have various different resistances which are experienced. Whereas at upper air, you don't have a resistance. Similarly, when we talk about the sea surface, have you come across a scenario that over the sea, suddenly in one portion, the water is very high in a cubical manner, and then their water is at a normal level? No, water is at the same level. So there is not significant amount of resistance at all. So when there is not significant resistance, the wind speed will be very high, isn't it? Over the sea surface, the friction is minimal. Means what? There is not much resistance offered to the wind. Whereas over the land area, there is significant resistance offered to the wind. That is why speed over the sea surface is high. Sea surface is high. Okay. Now, now we take a look at the aspect of onshore and offshore winds. So when we talk about onshore winds, these are basically the winds which move from portion of the water body to the land areas. So they move from water bodies to land areas. And again, I would like to reiterate, when we are talking about water bodies here, we will always be talking about seas and oceans. We are not going to talk about the small lakes, ponds in the backyard, bucket I had kept somewhere, the river which is moving near my house. We are not considering that. So onshore winds are those winds moving from the water bodies to the land area. For example, let's suppose a wind like this. Okay, from the water body to the land area. And offshore winds are the winds which move from basically land area to the water body. Okay, so that is basically onshore and offshore. Onshore winds, winds moving from a water body, oceans, to the land. Now, as the winds are moving over the water body, they will be able to pick up that moisture of the water body. And as they are able to pick that moisture, they will induce rainfall over the land area. So, basically, winds pick up moisture and bring rainfall. Okay? Whereas when we talk about offshore winds, so basically these are the winds which move from land to the sea. It is drier in nature and hence no rains. Okay, that is the basic characteristic of onshore and offshore winds. These are over a period of time, we will study about it and you will get an understanding about this as well, that these are responsible for causation of rainfall, occurrence of rainfall in different parts of the world in general. So in any part of the world, let's suppose here, if you consider the winds are coming like this, they will cause significant amount of rainfall in UK and in Western Europe. On the other hand, if the winds are moving like this, that means the region will be dry because the winds are coming from the land. They won't be able to pick up moisture. Okay. And no, it is not exactly land breeze and sea breeze. Land breeze and sea breeze, that exists in a very small distance, at max over a distance of 50 kilometers. Here we are talking about considerably large distances. The aspect of it is the movement is similar, but the causation of it, we will come to it. Okay. So now we come to the portion of air circulation. Why is it that air circulation does take place? Just a moment. So when we talk about air circulation, so why is it that air circulation does take place? So air circulation, basically, we have to understand that Earth is spherical. That means different areas, they receive uneven and unequal amount of heating in general. Some area might get very hot, some area might get very cold. So by the process of movement of air, you have that distribution of temperature which is achieved, that heat balance which is maintained. And that is where, if let's suppose the region of equator would continue to receive lot amount of heat and the region of poles, let's say, very little amount of heat, then what would be the consequence and circumstance or the outcome of it? Equator would keep on getting hotter and hotter, poles would keep on getting colder and colder, but you have a maintenance of temperature. That is because temperature is distributed across the planet. Now, there are various methodologies by which temperature is distributed. One of the methodologies is by the movement of oceanic water. Ocean water moves between different latitudes, mixing the water, mixing the temperature. The other more pertinent and more important methodology is actually the movement of air. When the air moves from a hotter region to a colder region, it warms that area, and vice versa effect is also true. So that is how heat distribution and temperature influence is experienced. Now here, when we take a look at it, basically, for air circulation, we have always understood that there is a wind which is in motion. Ever since you had the time of the ancient mariners and those sailors who would travel the world, the brave sailors who would travel the entirety of the world without the modern equipments, now they would be dependent on the wind. And they would always be sure that the wind is going to move, that is going to help the ships carry itself. Now, there has always been an attempt in order to understand why that wind is moving. So that is where, for the first time, when this entire wind circulation was postulated or was proposed, it was basically referred to as the unicellular model of circulation. Unicellular model of circulation. This was provided and postulated by Hadley. This was postulated by Hadley, and basically the basis of it was thermal pressure induced circulation. That's it. So basically what Hadley said was that, look, equator is going to be very warm, poles are going to be very, very cold. So if I consider this to be the equator, if I consider this to be the poles, now equator is very warm, winds will rise up, as they will rise up, eventually they will diverge after hitting the troposphere or the tropopause. As they diverge around the region of the poles, the temperature will be very low. So here there will be a sinking part of the convection current of the wind movement. And that is where here you will have a very high thermal pressure, a thermal high. And then this will come back. So that meant in one particular hemisphere, there was one cell of circulation as postulated. Hence the name, the case of unicellular model of circulation. But this model had a lot of flaws. For example, it was not possible for the air to have originated around the region of the poles and continue to move all the way till the region of equator. It is simply not possible. Because when you have or when you consider the movement across this large distance, right, when you consider the movement across this large distance, there will be many obstructions and their wind is nowhere as powerful to drive through thousands, these many thousands of kilometers without any kind of influence. The resistance will be so much, it will simply stop moving. So there was a flaw. And this flaw, for the first time, was significantly noticed by William Ferrel. Now, William Ferrel was an American climatologist, and he basically observed a few phenomena. He basically observed the fact that the wind movement, as per the unicellular model, wind movement on the surface should consistently be from the poles to equator, from the poles to the 0 degree. But Ferrel observed that in the middle latitudes, that is in between 40 degrees, 50 degrees, 60 degrees, in that region, the wind velocity or the wind movement is in the other direction. So that is where eventually another model of circulation was influenced or was given. And that was the more modern method which was accepted. And that is what was referred to as the tricellular model. So that is what was the tricellular model of circulation. Tricellular model. Now, what is this tricellular model? Let us try to understand that. So here we will consider only one hemisphere, the northern hemisphere. Southern hemisphere will be exactly similar. Now, let us consider 0 degree equator. Let us consider 30 degrees north, 60 degree north, and also 90 degree. Or let us do one thing. Instead, let us consider a zone. Somewhere in the region of 25 degree north to 30 degree north, in that region. Somewhere in the region of 55 degree north to 65 degree north. Thermal low is basically low pressure created due to heating. That is what is thermal low. Okay. Thermal high basically means the high pressure created due to colder condition. That is basically thermal high. Now, let us consider certain conditions here. Now, at 0 degree, on an average, the temperature will be high, isn't it? The temperature at 0 degree is normally going to be higher. Now, if the temperature at 0 degree is going to be higher, why is it going to be higher at 0 degree? 0 degree here refers to equator. I hope we understand that. Why is it that the temperature is going to be high at 0 degree? Because the rate of heating is going to be high. So as the rate of heating is going to be high, the land will get very warm. So the air above it, that will also get very warm. Now, when the air gets very, very warm, that air will tend to rise up. That air tends to rise up. And guys, please follow this slide or PPT for the next 10 to 15 minutes. Okay? Because this is going to be the essential feature important for the entirety of climatology, as far as even Indian monsoon, as far as even your beloved topic of cyclones. So even for that, you need this concept. Okay, so if you want to understand how cyclones occur, pay attention here. This is not about cyclones, but it will help you understand cyclones. So here, basically, the wind rises up after getting heated. Now, as this wind rises up, eventually it will hit the tropopause, right? Now, when it hits the tropopause, there will be a divergence. One will move to the southern hemisphere, another will move to the northern hemisphere. Now, let us follow the trajectory of this wind which is moving in upper atmosphere. Let us follow the trajectory of that wind. So, let's represent this planet. And here, we will just consider the upper air movement. Upper air movement, let's suppose. Now, in the upper air, if the wind is moving from the region of equator, will the wind experience Coriolis force or not? If the wind is moving from the region of equator in the upper air, will the wind experience Coriolis force or not? Yes, it will experience. Why won't the wind experience? Anything which is free from the ground surface will experience that Coriolis force. So in the northern hemisphere, it will bend to the right. So here, because we are considering upper air circulation, let me represent it by a different color so that you don't get confused. It will experience a deviation to the right. Now, with this deviation, do you think that the wind at all, ever, will the wind be able to reach at the poles with this deviation? Absolutely not. With this deviation, wind will start accumulating in this zone. In this zone, can we say there is an accumulation of the wind? There's an accumulation of wind here. Now, when there is an accumulation of wind in that region, means what? That wind will start staying in that region. It will start accumulating. Now, this is the top of troposphere, around the region of tropopause. So there, the temperature is significantly lower. So that means not only will the wind start accumulating there, there will also be cooling of the wind. Wind will become colder, heavier, and accumulated. So what will be the next course of action? Wind will start to sink. So here, I will repeat again. In the upper air, as the wind moves, one moves in the northern hemisphere, other moves to the southern hemisphere. So if you follow the path of the upper atmosphere wind, it will be deviating to the right. So it will end up accumulating in one region. As it begins to accumulate, eventually that wind will become heavier, colder also because it is at the height of tropopause, and it will start to sink. So this wind overall starts to sink. Now this sinks and falls on the ground surface. Now upon hitting the ground surface, here remember the example of the room that we had talked about. Upon hitting the ground surface, it will diverge, right? It will diverge here. One portion will go towards equator to fulfill the vacancy created at the region of equator. Similarly, you will observe the same phenomena in the southern hemisphere also, where the wind, after spending some time in the upper atmosphere, it will start cooling down, and due to Coriolis force, it is bending to the right in this case. So there will be significant accumulation in a region, and winds cannot progress beyond that. So any further winds which are coming from the region of equators, let's say this is the region of accumulated wind, which is already cold. Now, any further wind which is coming from this region will eventually end up accumulating, and all that accumulation eventually will lead to sinking because the winds are getting colder as well. So here, this is something which is observed in the southern hemisphere as well. Now, from both these areas, the winds, when they come to the equator, these winds will also get warmed up. They will also get heated up because high amount of solar insolation, and they will also start to rise up. Now, meanwhile, let's come to the region of the poles. Now, poles indicate very low temperature, significantly low temperature, -30, -40 degrees Celsius. So there, automatically, due to temperature conditions, you will have a high pressure. You will have a sinking air and a high pressure induced, because the temperature is very, very cold. So here you will have high pressure. Now, as this air is moving, it will come to lower latitude. It will progress. Meanwhile, this wind is also coming. Now what will happen? The winds are converging. They are colliding from both directions. Now what will happen? The wind has got no other place to go. The wind has no other place to go. So where the wind will go? The wind will rise up. Okay. The wind rises up. After it hits the tropopause, it will end up diverging. One portion goes here. It converges with the wind coming from the region of equator, the wind which was accumulating, and there will be convergence here, which will hit the ground, sink the ground, and then eventually on this side, the wind will diverge after hitting the tropopause and complete this. So here, what do you observe? In one hemisphere, that is from 0 degree onwards, in one hemisphere, you have 3 cells of circulation. Hence, a tricellular model of atmospheric circulation. I will repeat the entire process again, don't worry. But before that, let us think about the conditions of pressure. So suppose I consider that region of equator. Now, what do you think will be the pressure condition here? High pressure or low pressure? The wind is getting heated up and rising. So it will be high pressure, or rather it will be low pressure. And this is thermally induced. Okay. Now, in this region, the temperature is generally very high. But what is the condition of pressure here? What do you think? High pressure, isn't it? Because the wind is sinking here. So this is also what is referred to as subtropical high pressure belt. This is what is also referred to as equatorial low pressure. Then after that, what about this area? Here, what will be the pressure condition? Very good. It will be low pressure. So that will be subpolar low pressure zone. And this will be polar high. Okay. So these are what are referred to as the pressure zones. Let us repeat the entire concept again. And let us try to understand this entire process of circulation again. So it all is initiated, let's say, at the region of equator and at the region of the poles. So at the region of equator, when you have significant amount of heating of the landmass due to higher amount of insolation, the air above the landmass warms up quite significantly. And when the air warms up, the air tends to rise. The air tends to lift up. Now, as the air lifts up, it will continue to rise as long as it is warmer than the surrounding, as long as it is lighter than the surrounding. It will rise up. Eventually, it will hit the region of tropopause, right? Now, once it hits the tropopause, one will move to the portion of northern hemisphere, other will move to the region of southern hemisphere. Now here, if you take a look at the upper velocity or the upper atmospheric movement of the wind in the northern hemisphere, here, this is the movement of the wind happening at the region of tropopause almost. Now that virtually means what? If I consider the upper air movement of the wind, let's say I have to represent it here. So let's suppose this is the equator. The wind is rising up and is moving towards the northern hemisphere. So it will be bending to the right. It will be bending to the right. So over here, you will observe there is significant accumulation of wind in this region, isn't it? Wind will start getting accumulated. As the wind starts getting accumulated, then what happens? Then the wind eventually starts sinking here because the wind cannot move any further here. There is so much amount of deviation, the wind cannot move any further. It is not as if the wind can reach here, can it? Because the deviation to the right is so significant, wind cannot end up moving any further. So the wind starts sinking. Now, as the wind starts sinking, eventually it will hit the ground at around 25 degree to 30 degree north latitude. That is where it will end up hitting the ground. Now, when it hits the ground, it creates a high pressure on the ground surface. That is what is subtropical high pressure belt. Now, this pressure belt means that as the wind hits the ground, it then diverges. It diverges into the region of equator and into the region furthermore. Accumulation not getting, not able to imagine. Okay, fair enough. Why it will sink in the 25 to 30 degree latitude only? I understand, but in the northern hemisphere, the deflection towards right, you draw it in the left. Other doubts I can understand, but this doubt, right or left? Okay, one live example across the planet. You want me to give one live example of the planet? That is something which is okay. Fair enough. Hold your horses. So here, when you think about, let's suppose this particular area itself, or let me have a blank slide here. Suppose this is the planet. Now there is the equator, in the upper atmosphere, not on the surface, in the upper atmosphere, if the wind is moving from here in the northward direction, there will be a deviation to the right. Okay, deviation to the right means a deviation like this. So as the winds are getting deviated to the right, as the winds are getting deviated to the right, all these winds, they are originating from the equator. Can this wind reach here, this portion? All of those who had doubt in the upper atmosphere, that is Pulkit, Taras, Shalu, all of you. Can the wind reach here? Even if the wind tries to reach there, can it reach there? Think about it, let me know. Ashish, you also had doubt. No, right? The wind can never reach there, because for the wind to reach there, it needs to move across this path or this path, any of the path. But for all these paths, if you observe, the wind is basically deviating significantly. Even if the wind has to extend further, it will deviate furthermore due to Coriolis force. Isn't it? There will be a furthermore deviation due to Coriolis force. So this wind deviation is minimum at equator. This is not the equator that we are talking about. Are we talking about equator here? Equator is this one. We have already covered 25 to 30 degrees in that case. So there will be deviation, isn't it? So here in that case, so all of you who had a doubt that, so it is here that the Coriolis force is zero. Coriolis force is never going to be zero here. And in the, again, think about another aspect. The speed of the wind in the upper atmosphere. Will it be high? Will it be low? What do you think? Speed of wind in the upper atmosphere. Will it be high? Will it be low? Why low? Why do you think it will be low in the upper atmosphere? It will be very high. We have just seen at the concept. Wind velocity in the upper atmosphere is going to be very, very high because there is almost negligible force of friction, almost negligible resistance. That is why the wind velocity is very, very high. So all this wind is moving at a very high speed. That is why it will experience much higher amount of deviation. And all the meanwhile, it is getting cooled down at the region of the top of troposphere also. So what do you experience in this area? You experience that the wind cannot go any further. Because of the deviation, wind cannot move any further. Of deviation, wind cannot move any further. And which means what? As the wind cannot move any further, that means in this region, there will be an accumulation of wind, isn't it? That means there will be an accumulation of wind. Is that understood now? That why there will be an accumulation of wind? Ashutosh, you also had a problem here. All of you, please let me know. Is that understood now? So basically, there will be an accumulation of the wind here. And All the meanwhile, while the wind is accumulating, please understand that the region of the equator continues to receive that heat. The air continues to rise up, continues to push in that direction, and continues to accumulate furthermore. All the meanwhile, we are talking about the top of troposphere, very cold conditions. So not only will there be an accumulation of wind, there will be colder wind as well, isn't it? What will happen after that? This wind will be forced to sink down. There is no other region that the wind can go to. So that is why the wind here sinks down. Is that understood, everyone? Good. Right? Now, after that, as here it sinks down, it will hit the ground. And on the ground, roughly around 30-degree north latitude, that is where that sinking happens. Sometimes the sinking can happen at 25, sometime at 35. It can vary, but mostly at 30-degree north latitude, this sinking will happen. When this air then tends to sink, it hits the ground and creates a condition of high pressure. That is referred to as the subtropical high pressure zone. And after creating that high pressure, this then diverges. This diverges, and thereby it basically starts moving. Now, this 25-degree to 30-degree high pressure which is created, what kind of pressure is it? Is it thermal pressure or is it dynamic pressure? What do you think? This pressure which is created as a high pressure, is it thermal or is it dynamic? Good. It is going to be dynamic pressure, because here this high pressure is not created due to temperature. I hope we understand the difference between thermal and dynamic. Thermal means that is created by temperature effect. So colder areas high pressure, warmer areas low pressure. But when we say dynamic, it is created purely by sinking or rising of air due to wind movement. And here the sinking is happening because of wind movement. That is why here you will have a dynamic pressure, high pressure, which is created. So here, when we talk about it, here you will have a dynamic high pressure. And this wind then moves towards the polar region. And from the polar region, meanwhile, because it is very, very cold there, you have a thermal high pressure induced and created. So that polar wind will converge and collide with the warm tropical wind at around 55 to 60 degree. And as it collides there, it has got no other place to go. And that is where it starts to rise up. It starts to rise up. And that is where on the ground, it creates what? It creates a low pressure. And this is again, is it a thermal low pressure or is it a dynamic low pressure? What do you think? It is a dynamic low pressure. So here, because if the thermal low pressure, understand again, thermal means that low temperature will have high pressure, high temperature will have low pressure. It is controlled by temperature. Here it is a low pressure created only due to the movement of the wind. So the wind will rise up here due to convergence. So this will create a low pressure in this region. Now in this region, when there is a low pressure, air will rise up, it will diverge in the region of tropopause, and that is how the circulation is achieved. So this is basically the tricellular model of circulation in general. Now this is composed or comprised of three cells. One is the Hadley cell, one is the Ferrel cell, and then you have the polar cell. Okay. Now, again, I will reiterate. I understand many of you will have that doubt. Why only 30 degree? Why only 60 degree? Is there some almighty being sitting atop who is deciding only 30 degree and not 29 degree? So let me clarify. It is taken as an approx as 30 degree. It can happen at 25 degree also. It can happen at 35 degree also. Sometimes it can happen at 40 degree also. Sometimes it can happen at 20 degrees also. On an average, across the year, we take the average as 30 degree where this is sinking down. Okay, let me add that clarification because I'm sure I will have those questions which will follow. Okay, now here we have the Hadley cell, we have the Ferrel cell, and we have the polar cell, and these are your pressure zones. Now around the region of equator, so here you will have thermally induced pressure zones. Which are the thermally induced pressure zones? Thermal pressure zones here. You will have equatorial low, and polar high. These are thermal pressure zones. And then you have the dynamic pressure zones. Dynamic pressure zones created purely by the movement and aspect of the wind. That is subtropical high pressure and subpolar low. Okay. Now, in this case, if we consider the region around equator, now this is a thermally induced pressure zone. It will be induced when the temperature at the ground is very high, very warm. That is when this low pressure will be induced. Now, in this region, you have winds which are coming from both the tropics. Tropics means between the region of Tropic of Cancer and Tropic of Capricorn. So here you will have winds coming from both the tropics, isn't it? And they shall be converging, getting heated, and rising up. So in this case, that is why equatorial low is also what is referred to as the tropical convergence zone or intertropical convergence zone, that is ITCZ, because here you have winds coming from both the tropics converging and then rising up. So this is what is also referred to as intertropical tropical convergence zone. I hope we are comfortable up till this point. Now, let's elevate it a bit. So basically, all these pressure zones that you see, they are present across the planet. And that will induce a wind on the surface that you observe. And these are referred to as the planetary winds because they will also exist across the planet. So winds will blow from 30 to 0 or around 25 to 0 degree or ITCZ. Winds will blow from subtropical high pressure to the subpolar low pressure, from the polar high to the subpolar low pressure. That will be the surface movement of the wind. But then, are these pressure zones always going to be fixated in the same place? That only 30 degree, only 60 degree, we have decided this is the place, this is where we will be. No, it can happen. That, for example, when you have the June solstice is approaching and coming in front of us, 21st of June. 21st of June, virtually sun is directly overhead the Tropic of Cancer. So in that case, it might happen that the most active or intense thermal low pressure is not at equator. It can happen that the low pressure, let's say, gets created somewhere here. Rather than 0 degree, maybe 10 degree, maybe 12 degree, maybe 20 degree. That low pressure is created there. So that means the air will start rising in that case from this region. As it rises up, it will then diverge and it will sink somewhere here. Rather than 25, 35, it will sink maybe 40. And then furthermore, as it will diverge, it might rise up here. So all these pressure belts that you see, these pressure belts, they are prone to movement. They are prone to movement with the movement of the sun. As the sun tends to move, these pressure belts also moves. Let's suppose, again, when we talk about the winter condition, let's suppose the sun is somewhere here in the southern hemisphere. Now that means somewhere here will be the ITCZ, or the acute low pressure. That means the winds will be coming here, rising here, maybe sinking somewhere in 10, 20 degree, 25 degree. So that is where the pressure belts, they tend to shift in between the various season with the shifting of the zone of heating. The area which gets most heated up, generally you will find the ITCZ moving around that region, right? For example, right now, just to give you, I hope you don't get confused by it. Right now, if you think about it, ITCZ, rather than the equator, ITCZ is over India. ITCZ is over the central portion of India. It is advancing towards the central portion of India. Why? Because right now, as compared to the water in the Indian Ocean, India is much hotter, much warmer. And during the winter season, it will move to the southern hemisphere. So all the pressure belts, they shift along with these movement of the sun and the regions of heating and cooling. Okay. Now here, when we talk about it, then this is the case of the tricellular model, a kind of a well formatted diagram and image. So here you will observe that the winds on the surface, they end up moving from here to here, from here to here, and polar to subpolar region. Now the winds on the surface, they will also experience a kind of deviation due to Coriolis force, isn't it? They will also experience a deviation due to Coriolis force. Now let us think about from this image, because we have already drawn this large image. Let us at least make some utility out of it. Let us try to understand the wind movement. Now, let us consider this to be the subtropical high pressure belt. Let us consider here the subpolar low pressure belt. Actually, these belts are not the single line, they are a wide area that we talk about. Okay, a very wide area in general. Now, this is the ITCZ, or the intertropical convergence zone. This is the ITCZ here. This is the subtropical high. Subtropical high. This is the subpolar low. Low pressure. And this is where you have the polar high. Abhishek, the opposite of it is true. The winds, they end up creating very large waves, not the other way around. It is not going to be the case that large waves will create obstruction for the wind, but in fact, if the wind is strong, the waves will be larger. That is something that we study in the portion of oceanography. Okay. Now here, let us try to understand this. So here, on the surface, what do you observe? You observe basically, the basic facts is that the wind movement is going to have occur from 25 degree to 0 degree on the surface, isn't it? So let's draw that first. Or the subtropical high to 0 degree, that is 30 degree to 0 degree. So here, the wind would want to move from 30 degree to 0 degree but it is going to deviate to the right here. So the wind will be deviating to the right here. Now, winds are generally named after the direction from which they originate. That is the nomenclature followed for the naming of the winds anywhere. Similarly, in the southern hemisphere here also, but in this case, you will observe a leftward bend. So leftward bend like this, isn't it? Then after that, when we talk about here, the other wind from the subtropical high pressure, you observe that the other wind on the surface moves towards the subpolar low pressure. But here again, deviation to the right. So deviation to the right will happen. Deviation to the right will happen. Now, the other wind that you will observe is basically the case where it originates from the region of high pressure, that is polar high, and moves towards this low pressure region, isn't it? So that is basically where you will observe that it originates from the region of high pressure to the region of low pressure. So here, basically, you will observe it will move from that high pressure to the low pressure, but here it will have a deviation to the right. Isn't it? So these are basically the winds which are going to be prominent across the planet in both the hemispheres. And they are going to be present for the various different parts of the year throughout the planet. Hence, they are referred to as planetary winds because they are present across the planet, or permanent wind system. Now, they are named differently in different areas, for example, and they are named depending upon the region or the direction that they originate. For example, if you consider these winds, these are also what are referred to as trade winds, because historically, these are the winds which have significantly helped in carrying out the merchants carrying out the movement of the ships owing to this wind direction. Hence, they are referred to as trade winds in both the hemisphere, or simply trades. Now here, they originate from northeast direction and move to southwest direction. So that is why they are also what are referred to as northeast trades. Then in this region, you have the wind moving from west to east. That is where it is referred to as westerlies. Because they originate from west to east in general. Here in the region of the poles, here you will have the movement of the wind coming to from east to west. And that is why this is also what are referred to as polar easterlies. Okay, these are basically the permanent winds that you come across. Trade winds or northeast trades. In the southern hemisphere, you will have southeast to northwest. So this will be southeast trades. Winds are named from the region based upon the region from which they originate. That is why you have these kind of naming system. So basically, here you will observe that these winds, they are moving in the bending in the right direction in the northern hemisphere, bending towards the left direction in the southern hemisphere. Wherever they will move, they will bend to the right in the northern hemisphere, they will bend to the left in the southern hemisphere. So it is the subtropical high pressure belt where you have the winds moving in general. You will observe that from subtropical high pressure belt, The one part of the wind moves towards ITCZ, another part moves towards the 60-degree or subpolar region. Here also, from that subtropical high, one will move towards the subpolar, one will move towards the ITCZ. Then furthermore, you will observe that from the poles, the winds are moving to the region of the subpolar in this area. From the region of the poles, it is moving to the subpolar low. Here also from the poles to the subpolar low. So these are your permanent wind systems. Okay. These are surface winds of tricellular model, yes. At the tropopause, it's cooler condition, but we have already said that due to warmer air above, winds will diverge there. At tropopause, the winds, it's cooler conditions, but we have already said that due to warmer air above the tropopause, winds cannot rise any further, right? Because winds will rise as long as it is warmer. Above tropopause, you have stratosphere. Stratosphere is much warmer, so that is why the winds cannot rise any further. That is where the winds will start diverging. Okay? Is that understood, Vishnu? But earlier you draw trade wind in another direction. I did not draw the trade wind in earlier direction. Earlier, when you saw that, that was the upper air circulation that I was drawing. Upper air circulation and ground level circulation, that is going to be different. That is why I want to bring you to this image. When something is printed, generally we have lesser doubts. We have greater amount of reliance on something which is printed. So let me bring you to this image. This is where you have the trade winds, the westerlies, and the polar easterlies. It means winds become parallel to latitude due to forces, Coriolis forces. That is why it sinks down, correct or not? It doesn't exactly become parallel to latitude, but very similar, yes. It is not exactly parallel, but almost very similar. Is that understood? Right? So that is basically the permanent wind system. Now these pressure belts, they shift to the north during the summer season, they shift to the south during the winter season of the northern hemisphere because of the difference of heating and cooling by the sun. So that is where these pressure belts, they will be shifting to the north and south. You have shift of pressure belts. Okay. Now here, if you observe these pressure belts, these are given different names also. For example, when you consider the subtropical high pressure belt here, this one, this is also what is referred to as horse latitude. And the reason basically is a very silly anecdotal incidents about it. So here it is referred to as a horse latitude because wherever you have high pressure, in a region where you have high pressure, in a zone rather where you have a high pressure, right? So here as the air is sinking, you don't have any rainfall which occurs. This air sinks and then diverges. So on the ground, you have no air. Here, no air movement or no wind, and also no rains. So oftentimes when the sailors would traverse through this area, they would come across this area and they would come across this region, and where their ships, which would be aided by the wind, these ships could not progress any further. So that is why these ships basically would carry significant amount of horses. Also in those times people would carry horses because once you reach your destination you need to travel. Now they would carry these horses. Now many of these horses would be thrown overboard onto the water, not only to save the resources as the ship is lying stable and stagnant, but also to create some amount of ripple in the water so that the ship can move further. That is why this is the region which is referred to as the horse latitude. Then this is the low pressure or the ITCZ. This is the ITCZ. This is what is also referred to as doldrums. Doldrums because of lack of wind movement. Lack of wind movement. Why is there a lack of movement at the region of the doldrums? So here, basically, if you look at it in this region, let's suppose we are talking about the region of ITCZ. Now, in the region of ITCZ also, you will have winds which are coming and the winds that are rising up. Winds that are coming and the winds that are rising up. Now, if let's say you stand here in this area, you will experience very strong wind. If let's say you stand here in this region, here also you will experience very strong wind movement. But what if you are an individual who is standing here? Now, do you experience a wind movement in that area? No. So this is basically here a lack of wind movement in this region. There's a significant lack of wind movement in this area, and that is why it is referred to as a doldrum. Okay. So that is why we had the horse latitude, because in horse latitude also absolute calm conditions in the sense that you cannot have the situation where there's any wind movement. So oftentimes the ship would be stuck. They would have to throw the horses overboard, and that is where the name horse latitude came into existence. Okay. Now, after this, here, this is the image or the depiction of these pressure zones. Horse latitude, what do you have to understand? Do you have to understand how that high pressure is created, or do you have to understand the naming of high pressure or naming of horse latitude? Please clarify. Naming, I was certain people are more interested in the masala of it. Okay. Basically, the region of 30 degrees, this particular area, this is a region which has a high pressure. Now, wherever you have high pressure is always associated with a sinking of air column. With the high pressure, whenever you have a sinking air column. So if let's say you are present here, you will not experience any wind movement whatsoever. So you don't have any wind movement, you don't have any cloud formation, and no rainfall. High pressure regions are marked by a lack of rainfall, lack of cloud cover in general. So in the olden days, in the older time period, when you had the mariners and the merchants, they would travel by ships, the ships driven by the wind. The ships at that point of time did not have the diesel engines and the nuclear powered engines that you have now. They would be driven purely by the movement of the wind. So when these ships would come in this area, there would be a lack of wind and they would get stuck here for days altogether. They would get stuck here for many, many days, many weeks together. And that is where they would start running out of resources, because you are in the middle of the water, you don't have enough resources. Now, when you don't have enough resources, these ships would carry significant amount of horses at that point of time. Not only for the trading purposes, but even the merchants, the sailors, they would require horses once they would reach the ground. Now, in order to save the scarce resources that they had, scarce level of water, scarce level of food that they had, what they would do is basically they would throw these horses in the water. Now, when these horses would be thrown, not only would you save the resources on the ship, but at the same time, when you threw few of the horses together, that would create some ripple, some impact, some disturbance in the water, which could get the ship moving. Maybe the breeze could hold after that. And that is why this region basically started being referred to as the horse latitude. Okay? Is that understood? Okay. So just to clear, the horizontal movement of wind will be like arrows shown in the figure. Yes. Now these are your aspects of the pressure zones. So observe here, this is the during the time of the month of January. So these portions that you see, low pressure here that you see, this is your ITCZ. This is your ITCZ, right? So if you have to draw the belt of the ITCZ, it is somewhat like this, right? Air will rise here, will sink at the subpole, at the subtropical high pressure. Observe these high pressures. This is what is also referred to as Azores high, because this high pressure is created around the Azores island, right? You also have the Siberian high. Look at this, Hawaiian high. This is Hawaiian high. This is Azores high. Because this is created around Hawaiian Islands, this is created around the Azores Island, which is created, which is present. Here you have the South Pacific subtropical high. Here you have South Atlantic subtropical high. Here you have South Indian Ocean subtropical high. Then furthermore, if you will observe, here you have the subpolar low pressure belt. Here also you have subpolar low pressure belt, which is in existence. These are your subpolar low pressure belts. Here also, this is referred to as Aleutian low. This is the Icelandic low, depending upon the regions where these are created, right? So that is basically the pressure belt during the month of January. Observe, in the month of January, the southern hemisphere experiences winter condition. So southern hemisphere experiences summer conditions in the month of January. So southern hemisphere will get more heated up. That is why observe how the ITCZ bends towards the southern hemisphere. Now let us observe what happens during the month of July. So in the month of July, look at the ITCZ. Here you have the low pressure. Here you have the low pressure near the Sahara. Here you have the low pressure atop India. Here then again you have the low pressure. Here again you have the low pressure. So if you have to draw the line of the ITCZ or the zone of the ITCZ, it will be somewhat like this. It will be somewhat like this. So the belts have shifted north. The pressure belts have shifted north. Why? Because it is the month of July, heating of the northern hemisphere. So as a result of that, the Siberian high, which was present earlier, observe it has now disappeared because the wind cannot sink there anymore. Here you have the Azores high, the Hawaiian high. Here you have the low pressure, the subpolar low pressure, which is created in the southern hemisphere. This is the South Pacific subtropical high. So this is how, in reality, the pressure zones exist. It does not exist in reality like this. In reality, it does not exist like a plain band and winds moving in a straightforward direction. This is the real aspect of the pressure zones which are in existence. Okay. Now, after that, we have local winds, which we'll take a look at tomorrow. And we have a couple of questions initially itself that needs to be covered. So let us take a look at these questions. Normally, the temperature decreases with the increase in height from the Earth's surface because why? The atmosphere can be heated upwards only from the Earth's surface. there is more moisture in the upper atmosphere, the air is less dense in the upper atmosphere. So why is it that the temperature reduces as one moves away from the surface? Shruti, can we say that due to low pressure at equator, so the rotation of Earth at equator is more? No. Rotation will be the same, but the speed will be different because of the conditions of the distance covered at equator. Good. So here, the first option, that is the atmosphere can be heated upwards from the Earth's surface, that is correct. There is more moisture in the upper atmosphere, incorrect. Moisture is maximum in the lower atmosphere. The air is less dense in the upper atmosphere, that is correct. Meaning what? Meaning that there will be lesser retention of heat in the upper atmosphere. So the correct answer will be C, 1 and 3 only. Then another question, a variation of which was asked even in this year's prelims yesterday. The annual range of temperature. Annual range of temperature means variation of temperature between the summer and the winter. Annual range of temperature in the interior of the continents is high as compared to the coastal areas. That means that in the coastal areas, the temperature is more moderate, whereas in the interior areas, the temperature is more extreme. What is or are the reasons for the same? Thermal difference between land and water, variation in altitude between continents and oceans, presence of strong winds in the interior, or heavy rains in the interior as compared to the coastline. Which is the reason for a greater variation in temperature in the interior portion as compared to the coastal areas? Incorrect, Vivek. Good. Achal and Priyanka. So here, basically, when we consider why is it that this question basically refers to, if you infer that question correctly, it talks about why coastal areas have moderate temperature. So that is because there is a thermal difference between land and water, which induces wind movement, frequent wind movement, and that moderates the temperature. This is correct. Is it because there is a variation in altitude between continents and oceans? Absolutely not. Many of the areas in the continental sides or in the region of the coastline, they are at the same altitude. Then, if 2 is incorrect, now this year elimination method was not applicable. So let us take a look at all the options. Presence of strong winds in the interior. No, you have more strong winds in the coastal areas as compared to interior, right? So this is incorrect. Heavy rains in the interior. No, coastline will always experience heavy rains. So that is why the answer is A, that is 1 only. Okay. Now, that is where we'll end the session. We'll take a few questions now. How does low density imply low temperature? Shreyank, that is because when you have the conditions of low density, that means there is low retention of heat. Air is unable to retain heat and hence the lower temperature. Yes, the class session is over, so you can leave if you want. Shalu, please tell ITCZ is also called doldrum. It means doldrum is also shifting along with ITCZ. Okay. Shalu, think about it. A person is named Ram, and few of the people call him, let's say, XYZ. Now, if Ram moves, can we say XYZ has moved, or can we say that XYZ remained at home while Ram has gone to the market? No, if it is the same name, the doldrums also are shifting significantly. Why ITCZ moves up and down? That is basically because when we consider the ITCZ, it is an absolute low pressure, a thermal absolute low pressure. And that thermal absolute low pressure means the temperature should be very high. Now, during summer, temperature of water is high or temperature of land is high. Always land will get hotter. So that is why during summer, the ITCZ tends to move over the land area. Okay. I hope this is understood, Deepak. On one hand, at around 30-degree latitude, there is high pressure due to sinking air. And on the other hand, there is low pressure? No. At 30-degree Pulkit, there is no low pressure created. The temperature is high, but there is a high pressure along with the high temperature. That is why I told you temperature is one of the factors which can contribute to the. I will bring it back to the. That is why I write these things. I have written this thing. I don't know, somewhere along the line in the discussion we have forgotten this, but I have written this. Temperature is only one factor which induces a difference in pressure. It is not the contributing factor. Okay. So at the region of 30 degrees, you have a significant amount of high pressure which is created due to sinking air. Okay. There is a high temperature at 30 degree, but does not mean there will always be a low pressure wherever there is a high temperature. Can it important to remember this map in mains? Anjali, which map? Which we have not discussed any map today. Are you talking about the pressure gradient map? Absolutely not. That was just as an example. Okay. The same latitude at the southern hemisphere can be called a horse latitude? Yes, Arnab. Absolutely yes. Mohammed, UPSC completely removed elimination method. Now what should be our strategy? The strategy should be very simple. Cover the basics as soon as possible. Keep on revising them repeatedly. Keep an eye out on current affairs. Attack the questions, not the options. Okay, even this time you had the scope to get around 20-25 questions correct very easily, and the rest of them, next 30 to 40 ones, you could solve by application of logic, and that would be more than sufficient. So cover the basics. There is no shortcut, no two way around it. Okay, so that is something I would reinforce even till the last date before prelims. If you contact me, I will tell you the same thing. Cover the basics as soon as possible. Start with the process of revision, current affairs, and around 5 months or to 6 months before the prelims, start taking the prelims test series. This year, when the prelims test series was being conducted, we appealed to many of our students that please do take the test series in order to get the practice. And after yesterday, when we have been in touch with the candidates, we can see the marked difference amongst those who have taken the prelims test series, amongst those who have not practiced the test series. So that is a huge difference. So do take the test series, come what may. Okay. Now, how to connect all aspects when whatever done with UPSC paper. Jyoti, that will be once you are able to cover the entire subject, trust me, you will be able to look at the larger picture. Wait for that time. When we come to Indian geography, I will automatically help you connect with the various different issues. And Bhavna, does high density mean higher pressure? Yes. Abhishek, why Coriolis force is absent at equator? There is two cases of ahead and behind situation. Okay, excuse me. So if I take you to that particular portion, Abhishek, we have seen when objects move between similar speeds, there is no deviation. So if around the region of equator, we consider, let's say 5 degree north, 5 degrees south. So we can say that 5 degree north and 5 degree south will almost have the same radius as compared to equator. Now, when they will have the same radius, that means they will be rotating almost at the similar speed. So when there is a rotation at the similar speed, there is no deviation which happens, does it? And if there is no deviation, means no Coriolis force. That is why Coriolis force is absent at equator. Okay? Yes, Shalu. Doldrum means area of calm. Ocean, my doubt didn't get solved. Guys, please understand. In a 3.5 hour session, if you take a look at an average, we cover doubts for close to around 45 minutes to 50 minutes. Just take a look at the recording and the average. And still after that, you if you have that grievance, then what should we do? Should we cover 3.5 hour of doubts and then 15 minutes of teaching? Should we cover like that? We've tried to take as many doubts as possible. The subject matter experts are there to solve your doubts. They will be present half an hour further to take up your doubts. Even when the doubts are not covered, please write to us. Write to us at IES Live. We will get your doubts solved. Okay? For all those who are talking about the yesterday prelims paper discussion, that is something which is present in the YouTube. You can take a look at it, and that is where you can get an answer. Okay. How many questions needed to correct in order to pass prelims? Any idea? See, in general, you should have a score around, in today's context, you should have a score comfortably around 95 to 100 plus. So for that, overall, you need to be able to attempt around 70 to 75 questions, out of which close to around 55 need to be correct, and 20 you can commit a mistake in that. So that is where you will still be around 98. So 55 should be correct. That means in the first reading, get at least 35 correct, the easy ones, and then apply your logic to get and target the next one. Prelims test series will be present in the app, will be available in the app. In exam, do we have to draw diagrams in pen only? Pencil is also allowed if you have if you have time. Generally, in mains, you don't have time. There is no time in the mains, so that is why candidates will draw with pen only, provided it is neat. If you cannot draw neat diagram with pen, take a pencil, draw it with pencil. Okay. Yes, see, this year's prelims, the topics were much easier as compared to last year, Pulkit, but the option statements were much harder. That is why we are also predicting that the cutoff should drop at least by 4 to 5 marks. And given the fact that also the vacancy is higher this time. Why Azov Sea and Sea of Marmara is not called a gulf as it is surround? It is very small area. It is almost like an inland body ocean. That is why. That is why it is not called a gulf. Uh, to clear exam, we have to do practice of pre-series. Absolutely yes. Without prelims test series, please understand that in the present day context, it is almost impossible to clear the exam. So take the test series as much as possible. Jyoti, your question is that difference in pressure, is it? That is your question. What is wind movement is also another factor. And then you have written difference in pressure. And I'm unable to take a look at what the question is. Is it necessary to draw a curvy diagram of deviation? Absolutely, yes. Okay, Anshu, there is a bit of a holdup in that. Do contact the mentors and the mentorship. There's a bit of a holdup in that, as I'm aware. We'll get it resolved as soon. Yes, we will have the mains crash course. The mains test series will be initiated as soon as possible, as soon as this week itself. Okay. We have had many questions which have appeared, Hariom, from the portions of the revision series and the prelims test series. We have had many questions which have resembled, and the pattern has resembled more importantly. So, the purpose of prelims is to train you how to approach these questions. It is not that I have that question in the prelims test series, the same question has appeared. Look, so now if you take my test series, you will be able to clear. No, that is never the purpose of attempting prelims test series. That is where many of the candidates, when they take up the prelims test series, they, you will observe, they start rectifying the questions that UPSC will ask the same question. That is not, this is a kind of a class 10th level of approach, or even class 7th 8th level of approach. The purpose of the prelims test series is to train your mind, to condition your mind to sit stable for 2 hours without deviation, to apply concentration even if you know lesser amount, how to apply logic and still get the correct answer for a topic that I know and I know absolutely nothing about the options. That is the purpose of test series. The purpose of test series is to increase your knowledge for those areas. But still, having said that, there were questions which had appeared from that. Okay, so that is where we will restrict the session here, and we will meet again tomorrow to continue with the portion of local winds, and then after that, we will move on to precipitation. So, till that, take care of yourself. Goodbye. Thank you.